67. Hypothesis testing is used when a particular hypothesis about the true state of affairs is made by the analyst and data is gathered to determine whether that state of affairs is true or false. 68. 69. For example, the hypothesis might be that unemployment has no effect on inflation, which relates to an economics concept called the Phillips curve. 70. Hypothesis testing involves considering the likelihood of type 1 and type 2 errors, which relate to whether the data supports accepting or rejecting the hypothesis. 71. 72. Regression analysis may be used when the analyst is trying to determine the extent to which independent variable x affects dependent variable y, e.g., to what extent do changes in the unemployment rate x affect the inflation rate y. 73. This is an attempt to model or fit an equation line or curve for the data, such that y is a function of x. 74. 75. Necessary condition analysis (NCA) may be used when the analyst is trying to determine the extent to which independent variable x allows variable y, e.g., to what extent is a certain unemployment rate x necessary for a certain inflation rate y. 73. Whereas multiple regression analysis uses additive logic where each x variable can produce the outcome and the x's can compensate for each other, they are sufficient but not necessary. 76. Necessary condition analysis (NCA) uses necessity logic, where one or more x variables allow the outcome to exist, but may not produce it. They are necessary but not sufficient. Each single necessary condition must be present and compensation is not possible. 77. Analytical activities of data users. Analytic activities of data visualization users. Users may have particular data points of interest within a dataset, as opposed to the general messaging outlined above. Such low-level user analytic activities are presented in the following table. The task can also be organized by three poles of activities: retrieving values, finding data points, and arranging data points. 78, 79, 80, 81. Hash task. General description pro forma abstract examples. 1. Retrieve value. Given a set of specific cases, find attributes of those cases. What are the values of attributes x, y, z, in the data cases A, B, C? What is the mileage per gallon of the Ford Mondeo? How long is the movie Gone with the Wind? 2. Filter. Given some concrete conditions on attribute values, find data cases satisfying those conditions. Which data cases satisfy conditions A, B, C? What Kellogg's cereals have high fiber? What comedies have won awards? Which funds underperformed the SP 500? 3. Compute derived value. Given a set of data cases, compute an aggregate numeric representation of those data cases. What is the value of aggregation function f over a given set S of data cases? What is the average calorie content of Post cereals? What is the gross income of all stores combined? How many manufacturers of cars are there? 4. Find extremum. Find data cases possessing an extreme value of an attribute over its range within the dataset. What are the top, bottom, and data cases with respect to attribute A? What is the car with the highest MPG? What director film has won the most awards? What Marvel Studios film has the most recent release date? 5. Sort. Given a set of data cases, rank them according to some ordinal metric. What is the sorted order of a set S of data cases according to their value of attribute A? Order the cars by weight. Rank the cereals by calories. 6. Determine range. Given a set of data cases and an attribute of interest, find the span of values within the set. What is the range of values of attribute A in a set S of data cases? What is the range of film lengths? What is the range of car horsepowers? What actresses are in the dataset? 7. Characterize distribution. Given a set of data cases and a quantitative attribute of interest, characterize the distribution of that attribute's values over the set. What is the distribution of values of attribute A in a set S of data cases? What is the distribution of carbohydrates in cereals? What is the age distribution of shoppers? 8. Find anomalies. Identify any anomalies within a given set of data cases with respect to a given relationship or expectation, e.g. statistical outliers. Which data cases in a set S of data cases have unexpected, exceptional values? Are there exceptions to the relationship between horsepower and acceleration? Are there any outliers in protein? 9. Cluster. Given a set of data cases, find clusters of similar attribute values. Which data cases in a set S of data cases are similar in value for attributes x, y, z? Are there groups of cereals with similar fat, calories, sugar? Is there a cluster of typical film lengths? 10. Correlate. Given a set of data cases and two attributes, determine useful relationships between the values of those attributes. What is the correlation between attributes x and y over a given set S of data cases? Is there a correlation between carbohydrates and fat? Is there a correlation between country of origin and MPG? Do different genders have a preferred payment method? Is there a trend of increasing film length over the years? 11. Contextualization. 81. Given a set of data cases, find contextual relevancy of the data to the users. Which data cases in a set S of data cases are relevant to the current user's context? Are there groups of restaurants that have foods based on my current caloric intake? You are entitled to your own opinion, but you are not entitled to your own facts. Daniel Patrick Moynihan. Barriers to effective analysis may exist among the analysts performing the data analysis or among the audience. Distinguishing fact from opinion, cognitive biases, and innumeracy are all challenges to sound data analysis. 82. Confusing fact and opinion. Effective analysis requires obtaining relevant facts to answer questions, support a conclusion or formal opinion, or test hypotheses. 83. 84. Facts by definition are irrefutable, meaning that any person involved in the analysis should be able to agree upon them. 85. For example, in August 2010, the Congressional Budget Office, CBO, estimated that extending the Bush tax cuts of 2001 and 2003 for the 2011-2020 time period would add approximately $3.3 trillion to the national debt. 86. Everyone should be able to agree that indeed this is what CBO reported. They can all examine the report. This makes it a fact. Whether persons agree or disagree with the CBO is their own opinion. 87. As another example, the auditor of a public company must arrive at a formal opinion on whether financial statements of publicly traded corporations are fairly stated in all material respects. 88. This requires extensive analysis of factual data and evidence to support their opinion. When making the leap from facts to opinions, there is always the possibility that the opinion is erroneous. 89. Cognitive biases. There are a variety of cognitive biases that can adversely affect analysis. For example, confirmation bias is the tendency to search for or interpret information in a way that confirms one's preconceptions. 90. In addition, individuals may discredit information that does not support their views. 91. Analysts may be trained specifically to be aware of these biases and how to overcome them. 92. In his book Psychology of Intelligence Analysis, retired CIA analyst Richard Hoyer wrote that analysts should clearly delineate their assumptions and chains of inference and specify the degree and source of the uncertainty involved in the conclusions. 93. He emphasized procedures to help surface and debate alternative points of view. 94. Barriers to effective analysis. Numeracy. Effective analysts are generally adept with a variety of numerical techniques. However, audiences may not have such literacy with numbers or numeracy. They are said to be innumerate. 9. Person's communication. Since communicating the data may also be attempting to mislead or misinform, deliberately using bad numerical techniques. 96. For example, whether a number is rising or falling may not be the key factor. More important may be the number relative to another number, such as the size of government revenue or spending relative to the size of the economy (GDP), or the amount of cost relative to revenue in corporate financial statements. 97. This numerical technique is referred to as normalization. 25. Or common sizing. There are many such techniques employed by analysts, whether adjusting for inflation, i.e., comparing real versus nominal data, or considering population increases, demographics, etc. 98. Analysts apply a variety of techniques to address the various quantitative messages described in the section above. 99. Analysts may also analyze data under different assumptions or scenario. For example, when analysts perform financial statement analysis, they will often recast the financial statements under different assumptions to help arrive at an estimate of future cash flow, which they then discount to present value based on some interest rate, to determine the valuation of the company or its stock. 101. Similarly, the CBO analyzes the effects of various policy options on the government's revenue, outlays and deficits, creating alternative future scenarios for key measures. 102. Other topics. Smart buildings. A data analytics approach can be used in order to predict energy consumption in buildings. 103. The different steps of the data analysis process are carried out in order to realize smart buildings, where the building management and control operations including heating, ventilation, air conditioning, lighting and security are realized automatically by miming the needs of the building users and optimizing resources like energy and time. 104. Analytics and business intelligence. Analytics is the extensive use of data, statistical and quantitative analysis, explanatory and predictive models, and fact-based management to drive decisions and actions. It is a subset of business intelligence, which is a set of technologies and processes that uses data to understand and analyze business performance to drive decision-making. 105. Education. In education, most educators have access to a data system for the purpose of analyzing student data. 106. These data systems present data to educators in an over-the-counter data format, embedding labels, supplemental documentation, and a help system in making key package display and content decisions to improve the accuracy of educators' data analyses. 107. Practitioner notes. This section contains rather technical explanations that may assist practitioners but are beyond the typical scope of a Wikipedia article. 108. Initial data analysis. The most important distinction between the initial data analysis phase and the main analysis phase is that during initial data analysis one refrains from any analysis that is aimed at answering the original research question. 109. The initial data analysis phase is guided by the following 4 questions. 110. Quality of data. The quality of the data should be checked as early as possible. Data quality can be assessed in several ways, using different types of analysis: frequency counts, descriptive statistics, mean, standard deviation, median, normality, skewness, kurtosis, frequency histograms, normal imputation is needed. 111. Analysis of extreme observations. Outlying observations in the data are analyzed to see if they seem to disturb the distribution. 112. Comparison and correction of differences in coding schemes. Variables are compared with coding schemes of variables external to the dataset, and possibly corrected if coding schemes are not comparable. 113. Test for common method variance. The choice of analyses to assess the data quality during the initial data analysis phase depends on the analyses that will be conducted in the main analysis phase. 114. Quality of measurements. The quality of the measurement instruments should only be checked during the initial data analysis phase when this is not the focus or research question of the study. 115. 116. One should check whether structure of measurement instruments corresponds to structure reported in the literature. There are 2 ways to assess measurement quality. Confirmatory factor analysis. Analysis of homogeneity, internal consistency, which gives an indication of the reliability of a measurement instrument. 117. During this analysis, one inspects the variances of the items in the scales, the Cronbach's alpha of the scales, and the change in the Cronbach's alpha when an item would be deleted from a scale. 118. Initial transformations. After assessing the quality of the data and of the measurements, one might decide to impute missing data, or to perform initial transformations of one or more variables, although this can also be done during the main analysis phase. 119. Possible transformations of variables are 120. Square root transformation if the distribution differs moderately from normal. Log transformation if the distribution differs substantially from normal. Inverse transformation if the distribution differs severely from normal. Make categorical ordinal dichotomous if the distribution differs severely from normal, and no transformations help. Did the implementation of the study fulfill the intentions of the research design? One should check the success of the randomization procedure, for instance by checking whether background and substantive variables are equally distributed within and across groups. 121. If a study did not need or use a randomization procedure, one should check the success of the non-random sampling, for instance by checking whether all subgroups of the population of interest are represented in sample. 122. Other possible data distortions that should be checked are: dropout. This should be identified during the initial data analysis phase. Item non-response, whether this is random or not, should be assessed during the initial data analysis phase. Treatment quality using manipulation checks. 123. Characteristics of data sample. In any report or article, the structure of the sample must be accurately described. 124, 125. It is especially important to exactly determine the structure of the sample, and specifically the size of the subgroups when subgroup analyses will be performed during the main analysis phase. 126. The characteristics of the data sample can be assessed by looking at basic statistics of important variables, scatter plots, correlations and associations, cross-tabulations. 127. Final stage of the initial data analysis. During the final stage, the findings of the initial data analysis are documented, and necessary, preferable, and possible corrective actions are taken. 128. Also, the original plan for the main data analyses can and should be specified in more detail or rewritten. 129. In order to do this, several decisions about the main data analyses can and should be made. In the case of non-normals, should one transform variables, make variables categorical, ordinal, dichotomous, adapt the analysis method? In the case of missing data, should one neglect or impute the missing data, which imputation technique should be used? In the case of outliers, should one use robust analysis techniques? In case items do not fit the scale, should one adapt the measurement instrument by omitting items, or rather ensure comparability with other uses of the measurement instruments? In the case of two small subgroups, should one drop the hypothesis about intergroup differences, or use small sample techniques, like exact tests or bootstrapping? In case the randomization procedure seems to be defective, can and should one calculate propensity scores and include them as covariates in the main analyses? 130. Analysis. Several analyses can be used during the initial data analysis phase. 131. Univariate statistics, single variable. Bivariate associations, correlations. Graphical techniques, scatter plots. It is important to take the measurement levels of the variables into account for the analyses, as special statistical techniques are available for each level. 132. Nominal and ordinal variables. Quincey counts, numbers and percentages. Associations. Circumambulations, cross-tabulations. Hierarchical log linear analysis restricted to a maximum of 8 variables. Log linear analysis to identify relevant, important variables and possible confounders. Exact tests or bootstrapping in case subgroups are small. Computation of new variables. Continuous variables. Distribution. Statistics M, ST, variance, skewness, kurtosis. Stem and leaf displays. Box plots. Nonlinear analysis. Nonlinear analysis is often necessary when the data is recorded from a nonlinear system. Nonlinear systems can exhibit complex dynamic effects including bifurcations, chaos, harmonics and subharmonics that cannot be analyzed using simple linear methods. Nonlinear data analysis is closely related to nonlinear system identification. 133. Main data analysis. In the main analysis phase, analyses aimed at answering the research question are performed as well as any other relevant analysis needed to write the first draft of the research report. 134. Exploratory and confirmatory approaches. In the main analysis phase, either an exploratory or confirmatory approach can be adopted. Usually the approach is decided before data is collected. 135. In an exploratory analysis, no clear hypothesis is stated before analyzing the data, and the data is searched for models that describe the data well. 136. In a confirmatory analysis, clear hypotheses about the data are tested. 137. Exploratory data analysis should be interpreted carefully. When testing multiple models at once, there is a high chance on finding at least one of them to be significant, but this can be due to a type 1 error. 138. It is important to always adjust the significance level when testing multiple models with, for example, a Bonferroni correction. 139. Also, one should not follow up an exploratory analysis with a confirmatory analysis in the same dataset. In the main analysis phase, analyses aimed at answering the research question are performed as well as any other relevant analysis needed to write the first draft of the research report. 134. Exploratory and confirmatory approaches. In the main analysis phase, either an exploratory or confirmatory approach can be adopted. Usually the approach is decided before data is collected. 135. In an exploratory analysis, no clear hypothesis is stated before analyzing the data, and the data is searched for models that describe the data well. 136. In a confirmatory analysis, clear hypotheses about the data are tested. 137. Exploratory data analysis should be interpreted carefully. When testing multiple models at once, there is a high chance on finding at least one of them to be significant, but this can be due to a type 1 error. 138. It is important to always adjust the significance level when testing multiple models with, for example, a Bonferroni correction. 139. Also, one should not follow up an exploratory analysis with a confirmatory analysis in the same dataset. 140. An exploratory analysis is used to find ideas for a theory, but not to test that theory as well. 140. When a model is found exploratory in a dataset, then following up that analysis with a confirmatory analysis in the same dataset could simply mean that the results of the confirmatory analysis are due to the same type 1 error that resulted in the exploratory model in the first place. 140. The confirmatory analysis therefore will not be more informative than the original exploratory analysis. 141. Stability of results. It is important to obtain some indication about how generalizable the results are. 142. While this is often difficult to check, one can look at the stability of the results. Are the results reliable and reproducible? There are two main ways of doing that. 143. Cross-validation. By splitting the data into multiple parts, we can check if an analysis, like a fitted model based on one part of the data, generalizes to another part of the data as well. 144. Cross-validation is generally inappropriate, though, if there are correlations within the data, e.g. with panel data. 145. Hence other methods of validation sometimes need to be used. For more on this topic, see statistical model validation. 146. Sensitivity analysis. A procedure to study the behavior of a system or model when global parameters are systematically varied. One way to do that is via bootstrapping. 147. Free software for data analysis. Notable free software for data analysis include DevInfo, a database system endorsed by the United Nations Development Group for monitoring and analyzing human development. 148. Alki, data mining framework in Java with data mining-oriented visualization functions. 9. The Constans Information Miner, a user-friendly and comprehensive data analytics framework. Orange, a visual programming tool featuring interactive data visualization and methods for statistical data analysis, data mining, and machine learning. Pandas, Python library for data analysis. PA, Fortran, C data Notable free software for data analysis include DevInfo, a database system endorsed by the United Nations Development Group for monitoring and analyzing human development. 148. Alki, data mining framework in Java with data mining-oriented visualization functions. 9. The Constans Information Miner, a user-friendly and comprehensive data analytics framework. Orange, a visual programming tool featuring interactive data visualization and methods for statistical data analysis, data mining, and machine learning. Pandas, Python library for data analysis. PA, Fortran C data analysis framework developed at CERN. R, a programming language and software environment for statistical computing and graphics. 149. Root, C++ data analysis framework developed at CERN. SciPy, Python library for scientific computing. Julia, a programming language well suited for numerical analysis and computational science. Reproducible analysis. The typical data analysis workflow involves collecting data, running analyses through various scripts, creating visualizations, and writing reports. However, this workflow presents challenges, including a separation between analysis scripts and data, as well as a gap between analysis and documentation. Often, the correct order of running scripts is only described informally or resides in the data scientist's memory. The potential for losing this information creates issues for reproducibility. To address these challenges, it is essential to have analysis scripts written for automated, reproducible workflows. Additionally, dynamic documentation is crucial, providing reports that are understandable by both machines and humans, ensuring accurate representation of the analysis workflow even as scripts evolve. 150. International data analysis contests. Different companies or organizations hold data analysis contests to encourage researchers to utilize their data to solve a particular question using data analysis. 151. 152. A few examples of well-known international data analysis contests are as follows. 153. Kaggle competition, which is held by Kaggle. 154. LTPP data analysis contest held by FHWA and ASCE. 155. 156. Data mapping. In computing and data management, data mapping is the process of creating data element mappings between two distinct data models. Data mapping is used as a first step for a wide variety of data integration tasks, including 1. Data transformation or data mediation between a data source and a destination, identification of data relationships as part of data lineage analysis. Discovery of hidden sensitive data such as the last 4 digits of a social security number hidden in another user as part of a data masking or data identification project. Consolidation of multiple databases into a single database and identifying redundant columns of data for consolidation or elimination. For example, a company that would like to transmit and receive purchases and invoices with other companies might use data mapping to create data maps from a company's data to standardize ANSI ASC X12 messages for items such as purchase orders and invoices. Standards. X12 standards are generic electronic data interchange (EDI) standards designed to allow a company to exchange data with any other company, regardless of industry. The standards are maintained by the Accredited Standards Committee X12 ASC X12, with the American National Standards Institute ANSI accredited to set standards for EDI. The X12 standards are often called ANSI ASC X12 standards. The W3 introduced R2RML is a standard for mapping data in a relational database to data expressed in terms of the Resource Description Framework (RDF). In the future, tools based on semantic web languages such as RDF, the Web Ontology Language (OWL), and standardized metadata registry will make data mapping a more automatic process. This process will be accelerated if each application performed metadata publishing. Full automated data mapping is a very difficult problem. See semantic translation. Hand-coded, graphical manual. Data mappings can be done in a variety of ways using procedural code, creating XSLT transforms, or by using graphical mapping tools that automatically generate executable transformation programs. These are graphical tools that allow a user to draw lines from fields in one set of data to fields in another. Some graphical data mapping tools allow users to auto-connect a source and a destination. This feature is dependent on the source and destination data element name being the same. Transformation programs are automatically created in SQL, XSLT, Java, or C++. These kinds of graphical tools are found in most ETL, extract, transform, and load tools as the primary means of entering data maps to support data movement. Examples include SAP BODS and Informatica PowerCenter. Data-driven mapping. This is the newest approach in data mapping and involves simultaneously evaluating actual data values in two data sources using heuristics and statistics to automatically discover complex mappings between two datasets. This approach is used to find transformations between two datasets, discovering substrings, concatenations, arithmetic, case statements, as well as other kinds of transformation logic. This approach also discovers data exceptions that do not follow the discovered transformation logic. Semantic mapping. Semantic mapping is similar to the AutoConnect feature of data mappers, with the exception that a metadata registry can be consulted to look up data element synonyms. For example, if the source system lists first name but the destination lists person given name, the mappings will still be made if these data elements are listed as synonyms in the metadata registry. Semantic mapping is only able to discover exact matches between columns of data and will not discover any transformation logic or exceptions between columns. Data lineage is a track of the life cycle of each piece of data as it is ingested, processed, and output by the analytics system. This provides visibility into the analytics pipeline and simplifies tracing errors back to their sources. It also enables replaying specific portions or inputs of the data flow for stepwise debugging or regenerating lost output. In fact, database systems have used such information, called data provenance, to address similar validation and debugging challenges already. 2. See also. Data integration, data wrangling. Data and information visualization, data viz, or InfoVis, Vis 2, is the practice of designing and creating easy to communicate and easy to understand graphic or visual representations of a large amount. 3. Of complex quantitative and qualitative data and information with the help of static, dynamic or interactive visual items. Typically based on data and information collected from a certain domain of expertise, these visualizations are intended for a broader audience to help them visually explore and discover, quickly understand, interpret and gain important insights into otherwise difficult to identify structures, relationships, correlations, local and global patterns, trends, variations, constancy, clusters, outliers and unusual groupings within data. Exploratory visualization. 4, 5, 6. When intended for the general public, mass communication, to convey a concise version of known, specific information in a clear and engaging manner, presentational or explanatory visualization. 4. It is typically called information graphics. Statistician Professor Edward Tufte described Charles Joseph Menard's 1869 graphic of Napoleonic France's invasion of Russia as what may well be the best statistical graphic ever drawn, noting that it captures 6 variables in 2 dimensions. 1. Data visualization is concerned with visually presenting sets of primarily quantitative raw data in a schematic form. The visual formats used in data visualization include tables, charts and graphs, e.g. pie charts, bar charts, line charts, area charts, cone charts, pyramid charts, donut charts, histograms, spectrograms, cohort charts, waterfall charts, funnel charts, bullet graphs, etc., diagrams, plots, e.g. scatter plots, distribution plots, box and whisker plots, geospatial maps such as proportional symbol maps, choropleth maps, isopleth maps and heat maps, figures, correlation matrices, percentage gauges, etc., which sometimes can be combined in a dashboard. Information visualization, on the other hand, deals with multiple, large-scale and complicated datasets which contain quantitative numerical data as well as qualitative non-numerical, i.e. verbal or graphical, and primarily abstract information, and its goal is to add value to raw data, improve the viewer's comprehension, reinforce their cognition and help them derive insights and make decisions as they navigate and interact with the computer-supported graphical display. Visual tools used in information visualization include maps such as tree maps, animations, infographics, Sankey diagrams, flowcharts, network diagrams, semantic networks, entity relationship diagrams, Venn diagrams, timelines, mind maps, etc. Emerging technologies like virtual, augmented and mixed reality have the potential to make information visualization more immersive, intuitive, interactive and easily manipulable, and thus enhance the user's visual perception and cognition. 7. In data and information visualization, the goal is to graphically present and explore abstract, non-physical and non-spatial data collected from databases, information systems, file systems, documents, business data, etc. Presentational and exploratory visualization, which is different from the field of scientific visualization, where the goal is to render realistic images based on physical and spatial scientific data to confirm or reject hypotheses. Confirmatory visualization. 8. Effective data visualization is properly sourced, contextualized, simple and uncluttered. The underlying data is accurate and up-to-date to make sure that insights are reliable. Graphical items are well chosen for the given datasets and aesthetically appealing, with shapes, colors and other visual elements used deliberately in a meaningful and non-distracting manner. The visuals are accompanied by supporting text, labels and titles. These verbal and graphical components complement each other to ensure clear, quick and memorable understanding. Effective information visualization is aware of the needs and concerns and the level of expertise of the target audience, deliberately guiding them to the intended conclusion. 9. Such effective visualization can be used not only for conveying specialized, complex, big data-driven ideas to a wider group of non-technical audience in a visually appealing, engaging and accessible manner, but also to domain experts and executives for making decisions, monitoring performance, generating new ideas and stimulating research. 9. In addition, data scientists, data analysts and data mining specialists use data visualization to check the quality of data, find errors, unusual gaps and missing values in data, clean data, explore the structures and features of data and assess outputs of data-driven models. 4. In business, data and information visualization can constitute a part of data storytelling, where they are paired with a coherent narrative structure or storyline to contextualize the analyzed data and communicate the insights gained from analyzing the data clearly and memorably with the goal of convincing the audience into making a decision or taking an action in order to create business value. 3. This can be contrasted with the field of statistical graphics, where complex statistical data are communicated graphically in an accurate and precise manner among researchers and analysts with statistical expertise to help them perform exploratory data analysis or to convey the results of such analyses, where visual appeal, capturing attention to a certain issue and storytelling are not as important. 11. The field of data and information visualization is of interdisciplinary nature as it incorporates principles found in the disciplines of descriptive statistics, as early as the 18th century. 12. Visual communication, graphic design, cognitive science and, more recently, interactive computer graphics and human-computer interaction. 13. Since effective visualization requires design skills, statistical skills and computing skills, it is argued by authors such as Gershon and Page that it is both an art and a science. 14. The neighboring field of visual analytics marries statistical data analysis, data and information visualization and human analytical reasoning through interactive visual interfaces to help human users reach conclusions, gain actionable insights and make informed decisions which are otherwise difficult for computers to do. Research into how people read and misread various types of visualizations is helping to determine what types and features of visualizations are most understandable and effective in conveying information. 15. 16. On the other hand, unintentionally poor or intentionally misleading and deceptive visualizations, misinformative visualization, can function as powerful tools which disseminate misinformation, manipulate public perception and divert public opinion toward a certain agenda. 17. Thus data visualization literacy has become an important component of data and information literacy in the information age, akin to the roles played by textual, mathematical and visual literacy in the past. 18. Overview. Data visualization is one of the steps in analyzing data and presenting it to users. Partial map of the Internet early 2005 represented as a graph. Each line represents 2 IP addresses, and some delay between those 2 nodes. The field of data and information visualization has emerged from research in human-computer interaction, computer science, graphics, visual design, psychology, and business methods. It is increasingly applied as a critical component in scientific research, digital libraries, data mining, financial data analysis, market studies, manufacturing production control, and drug discovery. 19. Data and information visualization presumes that visual representations and interaction techniques take advantage of the human eye's broad bandwidth pathway into the mind to allow users to see, explore, and understand large amounts of information at once. Information visualization focuses on the creation of approaches for conveying abstract information in intuitive ways. 20. Data analysis is an indispensable part of all applied research and problem solving in industry. The most fundamental data analysis approaches are visualization, histograms, scatter plots, surface plots, tree maps, parallel coordinate plots, etc., statistics, hypothesis test, regression, PCA, etc., data mining, association mining, etc., and machine learning methods, clustering, classification, decision trees, etc. Among these approaches, information visualization, or visual data analysis, is the most reliant on the cognitive skills of human analysts, and allows the discovery of unstructured actionable insights that are limited only by human imagination and creativity. The analyst does not have to learn any sophisticated methods to be able to interpret the visualizations of the data. Information visualization is also a hypothesis generation scheme, which can be, and is typically followed by more analytical or formal analysis, such as statistical hypothesis testing. To communicate information clearly and efficiently, data visualization uses statistical graphics, plots, information graphics, and other tools. Numerical data may be encoded using dots, lines, or bars to visually communicate a quantitative message. 21. Effective visualization helps users analyze and reason about data and evidence. 22. It makes complex data more accessible, understandable. The greatest value of a picture is when it forces us to notice what we never expected to see. John Tukey, 27. And usable, but can also be reductive. 23. Users may have particular analytical tasks, such as making comparisons or understanding causality, and the design principle of the graphic, i.e., showing comparisons or showing causality, follows the task. Tables are generally used where users will look up a specific measurement, while charts of various types are used to show patterns or relationships in the data for one or more variables. Data visualization refers to the techniques used to communicate data or information by encoding it as visual objects, e.g., points, lines, or bars contained in graphics. The goal is to communicate information clearly and efficiently to users. It is one of the steps in data analysis or data science. According to Vitaly Friedman, 2008, the main goal of data visualization is to communicate information clearly and effectively through graphical means. It doesn't mean that data visualization needs to look boring to be functional or extremely sophisticated to look beautiful. To convey ideas effectively, both aesthetic form and functionality need to go hand in hand, providing insights into a rather sparse and complex dataset by communicating its key aspects in a more intuitive way. Yet designers often fail to achieve a balance between form and function, creating gorgeous data visualizations which fail to serve their main purpose, to communicate information. 24. Indeed, Fernanda Viegas and Martin M. Wattenberg suggested that an ideal visualization should not only communicate clearly, but stimulate viewer engagement and attention. 25. Data visualization is closely related to information graphics, information visualization, scientific visualization, exploratory data analysis, and statistical graphics. In the new millennium, data visualization has become an active area of research, teaching, and development. According to Post et al., 2002, it has united scientific and information visualization. 26. In the commercial environment, data visualization is often referred to as dashboards. Infographics are another very common form of data visualization. Characteristics of effective graphical displays. Edward Tufte has explained that users of information displays are executing particular analytical tasks such as making comparisons. The design principle of the information graphic should support the analytical task. 28. As William Cleveland and Robert McGill show. Principles. Different graphical elements accomplish this more or less effectively. For example, dot plots and bar charts outperform pie charts. 29. In his 1983 book The Visual Display of Quantitative Information, 30, Edward Tufte defines graphical displays and principles for effective graphical display in the following passage. Excellence in statistical graphics consists of complex ideas communicated with clarity, precision, and efficiency. Graphical displays should show the data. Inspire the viewer to think about the substance rather than about methodology, graphic design, the technology of graphic production, or something else. Avoid distorting what the data has to say. Present many numbers in a small space. Make large data sets coherent. Encourage the eye to compare different pieces of data. Reveal the data at several levels of detail, from a broad overview to the fine structure. Serve a reasonably clear purpose. Description, exploration, tabulation, or decoration be closely integrated with the statistical and verbal descriptions of a dataset. Graphics reveal data. Indeed, graphics can be more precise and revealing than conventional statistical computations. 31. For example, the Menard diagram shows the losses suffered by Napoleon's army in the 1812-1813 period. 6 variables are plotted: the size of the army, its location on a two-dimensional surface, x and y, time, the direction of movement, and temperature. The line width illustrates the comparison, size of the army at points in time, while the temperature axis suggests the cause of the change in army size. This multivariate display on a two-dimensional surface tells a story that can be grasped immediately while identifying the source data to build credibility. Tufte wrote in 1983 that, it may well be the best statistical graphic ever drawn. 31. Not applying these principles may result in misleading graphs, distorting the message, or supporting an erroneous conclusion. According to Tufte, chart junk refers to the extraneous interior decoration of the graphic that does not enhance the message or gratuitous three-dimensional or perspective effects. Needlessly separating the explanatory key from the image itself, requiring the eye to travel back and forth from the image to the key, is a form of administrative debris. The ratio of data to ink should be maximized, erasing non-data ink where feasible. 31. The Congressional Budget Office summarized several best practices for graphical displays in a June 2014 presentation. These included knowing your audience, b. designing graphics that can stand alone outside the report's context, and c. designing graphics that communicate the key messages in the report. 32. Quantitative messages. The same dataset plotted in 3. Charts. Top panel is a bar chart depicting the flow of occurrences over time, resembles the Sankey diagram in the New York Times original. 33. Middle panel is a bubble chart that separately quantifies discrete outcomes. Bottom panel is an exploded pie chart showing relative shares of categories, and shares within categories. Author Stephen Few described 8 types of quantitative messages that users may attempt to understand or communicate from a set of data and the associated graphs used to help communicate the message. 1. Time series. A single variable is captured over a period of time, such as the unemployment rate or temperature measures over a 10-year period. A line chart may be used to demonstrate the trend over time. 2. Ranking. Categorical subdivisions are ranked in ascending or descending order, such as a ranking of sales performance, the measure by salespersons, the category, with each salesperson a categorical subdivision, during a single period. A bar chart may be used to show the comparison across the salespersons. 3. Part to whole. Categorical subdivisions are measured as a ratio to the whole, i.e., a percentage out of 100%. A pie chart or bar chart can show the comparison of ratios, such as the market share represented by competitors in a market. 4. Deviation. Categorical subdivisions are compared against a reference, such as a comparison of actual versus budget expenses for several departments of a business for a given time period. A bar chart can show comparison of the actual versus the reference amount. 5. Frequency distribution shows the number of observations of a particular variable for given interval, such as the number of years in which the stock market return is between intervals such as 0-10%, 11-20%, etc. A histogram, a type of bar chart, may be used for this analysis. A box plot helps visualize key statistics about the distribution, such as median, quartiles, outliers, etc. 6. Correlation, comparison between observations represented by two variables x, y to determine if they tend to move in the same or opposite directions. For example, plotting unemployment x and inflation y for a sample of months. A scatter plot is typically used for this message. 7. Nominal comparison, comparing categorical subdivisions in no particular order, such as the sales volume by product code. A bar chart may be used for this comparison. 8. Geographic or geospatial, comparison of a variable across a map or layout, such as the unemployment rate by state or the number of persons on the various floors of a building. A cartogram is a typical graphic used. 2134. Analysts reviewing a set of data may consider whether some or all of the messages and graphic types above are applicable to their task and audience. The process of trial and error to identify meaningful relationships and messages in the data is part of exploratory data analysis. Visual perception and data visualization. A human can distinguish differences in line length, shape, orientation, distances, and color hue readily without significant processing effort. These are referred to as pre-attentive attributes. For example, it may require significant time and effort, attentive processing, to identify the number of times a digit, 5, appears in a series of numbers, but if that digit is different in size, orientation, or color, instances of the digit can be noted quickly through pre-attentive processing. 35 compelling graphics take advantage of pre-attentive processing and attributes and the relative strength of these attributes. For example, since humans can more easily process differences in line length and surface area, it may be more effective to use a bar chart, which takes advantage of line length to show comparison, rather than pie charts, which use surface area to show comparison. 35. Human perception, cognition and data visualization. Almost all data visualizations are created for human consumption. Knowledge of human perception and cognition is necessary when designing intuitive visualizations. 36. Cognition refers to processes in human beings like perception, attention, learning, memory, thought, concept formation, reading, and problem solving. 37. Human visual processing is efficient in detecting changes and making comparisons between quantities, sizes, shapes and variations in lightness. When properties of symbolic data are mapped to visual properties, humans can browse through large amounts of data efficiently. It is estimated that 2/3 of the brain's neurons can be involved in visual processing. Proper visualization provides a different approach to show potential connections, relationships, etc., which are not as obvious in non-visualized quantitative data. Visualization can become a means of data exploration. Studies have shown individuals use on average 19% less cognitive resources, and 4.5% better able to recall details when comparing data visualization with text. 38. History. Selected milestones and inventions. The modern study of visualization started with computer graphics, which has from its beginning been used to study scientific problems. However, in its early days the lack of graphics power often limited its usefulness. The recent emphasis on visualization started in 1987 with the special issue of Computer Graphics on Visualization in Scientific Computing. Since then there have been several conferences and workshops, co-sponsored by the IEEE Computer Society and ACM SIGGRAPH. 39. They have been devoted to the general topics of data visualization, information visualization and scientific visualization, and more specific areas such as volume visualization. In 1786, William Playfair published the first presentation graphics. Product space localization, intended to show the economic complexity of a given economy. Tree map of Benin exports 2009 by product category. The product exports tree maps are one of the most recent applications of these kind of visualizations, developed by the Harvard-MIT Observatory of Economic Complexity. There is no comprehensive history of data visualization. There are no accounts that span the entire development of visual thinking and the visual representation of data, in which collate the contributions of disparate disciplines. 40. Michael Friendly and Daniel J. Dennis of York University are engaged in a project that attempts to provide a comprehensive history of visualization. Contrary to general belief, data visualization is not a modern development. Since prehistory, stellar data, or information such as location of stars were visualized on the walls of caves, such as those found in Lascaux Cave in southern France since the Pleistocene era. 41. Physical artifacts such as Mesopotamian clay tokens 5500 BC, Inca quipus 2600 BC, and Marshall Islands stick charts N.D. can also be considered as visualizing quantitative information. 42. 43. The first documented data visualization can be tracked back to 1160 BC with Turin Papyrus map which accurately illustrates the distribution of geological resources and provides information about quarrying of those resources. 44. Such maps can be categorized as thematic cartography, which is a type of data visualization that presents and communicates specific data and information through a geographical illustration designed to show a particular theme connected with a specific geographic area. Earliest documented forms of data visualization were various thematic maps from different cultures and ideograms and hieroglyphs that provided an allowed interpretation of information illustrated. For example, linear bead tablets of Mycenae provided a visualization of information regarding late Bronze Age era trades in the Mediterranean. The idea of coordinates was used by ancient Egyptian surveyors in laying out towns. Earthly and heavenly positions were located by something akin to latitude and longitude at least by 200 BC, and the map projection of a spherical Earth into latitude and longitude by Claudius Ptolemy circa 85 c. 165 in Alexandria would serve as reference standards until the 14th century. 44. The invention of paper and parchment allowed further development of visualizations throughout history. Figure shows a graph from the 10th or possibly 11th century that is intended to be an illustration of the planetary movement, used in an appendix of a textbook in monastery schools. 45. The graph apparently was meant to represent a plot of the inclinations of the planetary orbits as a function of the time. For this purpose, the zone of the zodiac was represented on a plane with a horizontal line divided into 30 parts as the time or longitudinal axis. The vertical axis designates the width of the zodiac. The horizontal scale appears to have been chosen for each planet individually, for the periods cannot be reconciled. The accompanying text refers only to the amplitudes. The curves are apparently not related in time. Planetary movements. By the 16th century, techniques and By the 16th century, techniques and instruments for precise observation and measurement of physical quantities, and geographic and celestial position were well developed. For example, a wall quadrant, constructed by Tycho Brahe 1546-1601 covering an entire wall in his observatory. Particularly important were the development of triangulation and other methods to determine mapping locations accurately. 40. Very early, the measure of time led scholars to develop innovative way of visualizing the data, e.g. Lorenz Kodoman in 1596, Johannes Temporius in 1596-46. French philosopher and mathematician René Descartes and Pierre de Fermat developed analytic geometry and two-dimensional coordinate system which heavily influenced the practical methods of displaying and calculating values. Fermat and Blaise Pascal's work on statistics and probability theory laid the groundwork for what we now conceptualize as data. 40. According to the Interaction Design Foundation, these developments allowed and helped William Playfair, who saw potential for graphical communication of quantitative data, to generate and develop graphical methods of statistics. 36. Playfair time series. In the second half of the 20th century, Jacques Bertin used quantitative graphs to represent information, intuitively, clearly, accurately, and efficiently. 36. John Tukey and Edward Tufte pushed the bounds of data visualization. Tukey with his new statistical approach of exploratory data analysis and Tufte with his book, The Visual Display of Quantitative Information, paved the way for refining data visualization techniques for more than statisticians. With the progression of technology came the progression of data visualization, starting with hand-drawn visualizations and evolving into more technical applications, including interactive designs leading to software visualization. 47. Programs like SAS, SOFA, R, Minitab, Cornerstone and more allow for data visualization in the field of statistics. Other data visualization applications, more focused and unique to individuals, programming languages such as D3, Python and JavaScript help to make the visualization of quantitative data a possibility. Private schools have also developed programs to meet the demand for learning data visualization and associated programming libraries, including free programs like the Data Incubator or paid programs like General Assembly. 48. Beginning with the symposium, Data to Discovery, in 2013, Art Center College of Design, Caltech and JPL in Pasadena have run an annual program on interactive data visualization. 49. The program asks, how can interactive data visualization help scientists and engineers explore their data more effectively? How can computing, design, and design thinking help maximize research results? What methodologies are most effective for leveraging knowledge from these fields? By encoding relational information with appropriate visual and interactive characteristics to help interrogate, and ultimately gain new insight into data, the program develops new interdisciplinary approaches to complex science problems, combining design thinking and the latest methods from computing, user-centered design, interaction design and 3D graphics. Terminology. Data visualization involves specific terminology, some of which is derived from statistics. For example, author Stephen Few defines two types of data, which are used in combination to support a meaningful analysis or visualization. Categorical, represent groups of objects with a particular characteristic. Categorical variables can either be nominal or ordinal. Nominal variables, for example gender, have no order between them and are thus nominal. Ordinal variables are categories within order, for sample recording the age groups and one falls into. 50. Quantitative, represent measurements, such as the height of a person or the temperature of an environment. Quantitative variables can either be continuous or discrete. Continuous variables capture the idea that measurements can always be made more precisely, while discrete variables have only a finite number of possibilities, such as a count of some outcomes or an age measured in whole years. 50. The distinction between quantitative and categorical variables is important because the two types require different methods of visualization. Two primary types of information displays are tables and graphs. A table contains quantitative data organized into rows and columns with categorical labels. It is primarily used to look up specific values. In the example above, the table might have categorical column labels representing the name, a qualitative variable, and age, a quantitative variable, with each row of data representing one person, the sampled experimental unit or category subdivision. A graph is primarily used to show relationships among data and portrays values encoded as visual objects, e.g., lines, bars, or points. Numerical values are displayed within an area delineated by one or more axes. These axes provide scales, quantitative and categorical, used to label and assign values to the visual objects. Many graphs are also referred to as charts. 51. Epler and Lengler have developed a periodic table of visualization methods, an interactive chart displaying various data visualization methods. It includes 6 types of data visualization methods: data, information, concept, strategy, metaphor, and compound. 52. In Visualization Analysis and Design, Tamara Munzner writes, computer-based visualization systems provide visual representations of datasets designed to help people carry out tasks more effectively. Munzner argues that visualization is suitable when there's a need to augment human capabilities rather than replace people with computational decision-making methods. 53. Name visual dimensions description, example usages. Bar chart of tips by day of week. Bar chart. Length count category. Color. Presents categorical data with rectangular bars with heights or lengths proportional to the values that they represent. The bars can be plotted vertically or horizontally. Bar graph shows comparisons among discrete categories. One axis of the chart shows the specific categories being compared, and the other axis represents a measured value. Some bar graphs present bars clustered in groups of more than one, showing the values of more than one measured variable. These clustered groups can be differentiated using color. For example, comparison of values, such as sales performance for several persons or businesses in a single time period. Variable with bar chart relating. Population along x-axis. Per person. Emissions 1990-2018 along y-axis and total emissions area as xy product of values. Variable with very wide bar chart hmons. Wikimedia.org/wiki category variable e with _bar_ charts. Category. Size count extent in first dimension, size count extent in second dimension. Size count extent is area of bar color. Includes most features of basic bar chart. Above areas of non-uniform width bars represent quantities with areas that are respective products of related pairs of vertical axis quantities a x and horizontal axis quantities x. Arithmetically, a x asterisk x equals a for each bar. Instances: mosaic plots, also known as Marimekko or Mekko charts. Techniques. Projected 1. Frequency and 2. Intensity of extreme, 10-year heat waves are connected in pairs of horizontal and vertical bars, respectively. Bars are distinguished by 3. Color-coded. Primary category: degree of global warming. Orthogonal composite bar chart. Numerical value of first variable. Extent in first dimension. Superimposed horizontal bars, numerical value of second variable, extent in second dimension, like conventional. Vertical bar chart, category for first and second. Variables, e.g., color-coded includes most features of basic bar chart, above pairs of numeric variables, usually color-coded, rendered by category. Variables need not be directly related in the way they are in very wide charts. Histogram of housing prices, histogram. Bin limits. Count, length, color. An approximate representation of the distribution of numerical data. Divide the entire range of values into a series of intervals and then count how many values fall into each interval. This is called binning. The bins are usually specified as consecutive, non-overlapping intervals of a variable. The bins intervals must be adjacent, and are often but not required to be of equal size. For example, determining frequency of annual stock market percentage returns within particular ranges, bins such as 0-10%, 11-20%, etc. The height of the bar represents the number of observations, years, with a return percent in the range represented by the respective bin. A scatterplot. Showing negative correlation between two variables. Scatterplot. Plot, x position, y position. Symbol, glyph, color. Size. Uses Cartesian coordinates to display values for typically two variables for a set of data. Points can be coded via color, shape and/or size to display additional variables. Each point on the plot has an associated x and y term that determines its location on the Cartesian plane. Scatterplots are often used to highlight the correlation between variables x and y. Also called dot plots. Scatterplot. Scatterplot 3D. Position x, position y, position z, color. Symbol, size. Similar to the two-dimensional scatterplot above, the three-dimensional scatterplot visualizes the relationship between typically three variables from a set of data. Again, point can be coded via color, shape and/or size to display additional variables. Network analysis. Network. Node size, nodes, color, ties, thickness, ties, color. Spatialization, finding clusters in the network, e.g. grouping Facebook friends into different clusters. Discovering bridges, information brokers or boundary spanners between clusters in the network. Determining the most influential nodes in the network, e.g. a company wants to target a small group of people on Twitter for a marketing campaign. Finding outlier actors who do not fit into any cluster or are in the periphery of a network. Pie chart. Pie chart, color. Represents one categorical variable which is divided into slices to illustrate numerical proportion. In a pie chart, the arc length of each slice and consequently its central angle and area is proportional to the quantity it represents. For example, as shown in the graph to the right, the proportion of English native speakers worldwide. Line chart. Line chart. X position, Y position. Symbol, glyph, color. Size. Represents information as a series of data points called markers connected by straight line segments. Similar to a scatter plot except that the measurement points are ordered typically by their x-axis value and joined with straight line segments. Often used to visualize a trend in data over intervals of time, a time series, thus the line is often drawn chronologically. A log-log chart. Spanning more than one order of magnitude along both axes. Semi-log or log-log nonlinear charts x position, y position. Symbol, glyph, color. Connections represents data as lines or series of points spanning large ranges on one or both axes. One or both axes are represented using a nonlinear logarithmic scale. Stream graph. Stream graph, type of area chart. Width. Color. Time flow, a type of stacked area chart that is displaced around a central axis, resulting in a flowing shape. Unlike a traditional stacked area chart in which the layers are stacked on top of an axis, in a stream graph the layers are positioned to minimize their wiggle. Stream graphs display data with only positive values, and are not able to represent both negative and positive values. Example, the visual shows music listened to by a user over time. Tree map. Tree map. Size color is a method for displaying hierarchical data using nested figures, usually rectangles. For example, disk space by location, file type. Gantt chart. Gantt chart. Color. Time flow, type of bar chart that illustrates a project schedule. Modern Gantt charts also show the dependency relationships between activities and current schedule status. For example, used in project planning. Heat map. Heat map. Color. Categorical variable. Represents the magnitude of a phenomenon as color in two dimensions. There are two categories of heat maps. Cluster heat map, where magnitudes are laid out into a matrix of fixed cell size whose rows and columns are categorical data. For example, the graph to the right. Spatial heat map, where no matrix of fixed cell size, for example a heat map. For example, a heat map showing population densities displayed on a geographical map. Stripe graphic. Stripe graphic. X position, color. A sequence of colored stripes visually portrays trend of a data series. Portrays a single variable, prototypically temperature over time to portray global warming, deliberately minimalist, with no technical indicia, to communicate intuitively with non-scientists. 54. Can be stacked to represent plural series. Example. Animated spiral graphic. Animated. Spiral graphic, radial distance dependent variable. Rotating angle, cycling through months. Color, passing years. Portrays a single dependent variable, prototypically temperature over time to portray global warming. Dependent variable is progressively plotted along a continuous spiral, determined as a function of a constantly rotating angle, 12 months per revolution, and b evolving color. Color changes over passing years. 55. Box and whisker plot. Box and whisker plot, x-axis, y-axis, a method for graphically depicting groups of numerical data through their quartiles. Box plots may also have lines extending from the box's whiskers, indicating variability outside the upper and lower quartiles. Outliers may be plotted as individual points. The two boxes graphed on top of each other represent the middle 50% of the data, with the line separating the two boxes identifying the median data value, and the top and bottom edges of the boxes represent the 75th and 25th percentile data points respectively. Box plots are non-parametric. They display variation in samples of a statistical population without making any assumptions of the underlying statistical distribution, thus are useful for getting an initial understanding of a dataset. For example, comparing the distribution of ages between a group of people, e.g., male and females. Flowchart. Flowchart. Workflow or process. Represents a workflow, process or a step-by-step approach to solving a task. The flowchart shows the steps as boxes of various kinds, and are ordered by connecting the boxes with arrows. For example, outlining the actions to undertake if a lamp is not working, as shown in the diagram to the right. Radar chart. Radar chart. Attributes. Value assigned to attributes. Displays multivariate data in the form of a two-dimensional chart of 3 or more quantitative variables represented on axes starting from the same point. The relative position and angle of the axes is typically uninformative, but various heuristics, such as algorithms that plot data as the maximal total area, can be applied to sort the variables' axes into relative positions that reveal distinct correlations, trade-offs, and a multitude of other comparative measures. For example, comparing attributes, skills, e.g., communication, analytical, IT skills learned across different university degrees, e.g., mathematics, economics, psychology. Venn diagram. Venn diagram all possible logical relations between a finite collection of different sets. Shows all possible logical relations between a finite collection of different sets. These diagrams depict elements as points in the plane, and sets as regions inside closed curves. A Venn diagram consists of multiple overlapping closed curves, usually circles, each representing a set. The points inside a curve labeled S represent elements of the set S, while points outside the boundary represent elements not in the set S. This lends itself to intuitive visualizations. For example, the set of all elements that are members of both sets S and T, denoted S intersection T in red. The intersection of S and T is represented visually by the area of overlap of the regions S and T in Venn diagrams. The curves are overlapped in every possible way, showing all possible relations between the sets. Iconography of correlations. Iconography of correlations. No axis. Solid line. Dotted line. Color. Exploratory data analysis. Replace a correlation matrix by a diagram where the remarkable correlations are represented by a solid line, positive correlation, or a dotted line, negative correlation. Points can be coded via color. Other techniques. Cartogram. Cladogram. Phylogeny. Concept mapping. Dendrogram. Classification. Information visualization. Reference model. Grand tour. Graph drawing. Heat map. Hyperbolic tree. Multidimensional scaling. Parallel coordinates. Problem-solving environment. Tree mapping. Interactivity. Interactive data visualization enables direct actions on a graphical plot to change elements and link between multiple plots. 56. Interactive data visualization has been a pursuit of statisticians since the late 1960s. Examples of the developments can be found on the American Statistical Association Video Lending Library. 57. Common interactions include brushing, works by using the mouse to control a paintbrush, directly changing the color or glyph of elements of a plot. The paintbrush is sometimes a pointer and sometimes works by drawing an outline of sorts around points. The outline is sometimes irregularly shaped, like a lasso. Brushing is most commonly used when multiple plots are visible and some linking mechanism exists between the plots. There are several different conceptual models for brushing and a number of common linking mechanisms. Brushing scatterplots can be a transient operation in which points in the active plot only retain their new characteristics. At the same time, they are enclosed or intersected by the brush, or it can be a persistent operation, so that points retain their new appearance after the brush has been moved away. Transient brushing is usually chosen for linked brushing, as we have just described. Painting. Persistent brushing is useful when we want to group the points into clusters and then proceed to use other operations, such as the tour, to compare the groups. It is becoming common terminology to call the persistent operation painting. Identification, which could also be called labeling or label brushing, is another plot manipulation that can be linked. Bringing the cursor near a pointer edge in a scatterplot, or a bar in a bar chart, causes a label to appear that identifies the plot element. It is widely available in many interactive graphics, and is sometimes called mouse over. Scaling, maps the data onto the window, and changes in the area of the mapping function help us learn different things from the same plot. Scaling is commonly used to zoom in on crowded regions of a scatterplot, and it can also be used to change the aspect ratio of a plot, to reveal different features of the data. Linking, connects elements selected in one plot with elements in another plot. The simplest kind of linking, one-to-one, where both plots show different projections of the same data, and a point in one plot corresponds to exactly one point in the other. When using area plots, brushing any part of an area has the same effect as brushing it all and is equivalent to selecting all cases in the corresponding category. Even when some plot elements represent more than one case, the underlying linking rule still links one case in one plot to the same case in other plots. Linking can also be by categorical variable, such as by a subject id, so that all data values corresponding to that subject are highlighted, in all the visible plots. Other perspectives. There are different approaches on the scope of data visualization. One common focuses on information presentation, such as Friedman 2008. Friendly 2008 presumes two main parts of data visualization, statistical graphics and thematic cartography. 58 in this line the data visualization, modern approaches, 2007 article gives an overview of 7 subjects of data visualization. 59. Articles and resources. Displaying connections. Displaying data. Displaying news. Displaying websites. Mind maps. Tools and services. All these subjects are closely related to graphic design and information representation. On the other hand, from a computer science perspective, Fritz H. Post in 2002 categorized the field into subfields. 2660. Information visualization. Interaction techniques and architectures. Modeling techniques. Multi-solution methods. Visualization algorithms and techniques. Volume visualization. Within the Harvard Business Review, Scott Barinato developed a framework to approach data visualization. 61. To start thinking visually, users must consider 2 questions. 1. What you have and 2. What you're doing. The first step is identifying what data you want visualized. It is data-driven like profit over the past 10 years or a conceptual idea like how specific organization is structured. Once this question is answered, one can then focus on whether they are trying to communicate information, declarative visualization, or trying to figure something out, exploratory visualization. Scott Barinato combines these questions to give 4 types of visual communication that each have their own goals. 61. These 4 types of visual communication are as follows. Idea illustration, conceptual and declarative. 61. Used to teach, explain and or simply concepts. For example, organization charts and decision trees. Idea generation, conceptual and exploratory. 61. Used to discover, innovate and solve problems. For example, a whiteboard after a brainstorming session. Visual discovery, data-driven and exploratory. 61. Used to spot trends and make sense of data. This type of visual is more common with large and complex data where the dataset is somewhat unknown and the task is open-ended. Everyday data visualization, data-driven and declarative. 61. The most common and simple type of visualization used for affirming and setting context. For example, a line graph of GDP over time. Applications. Data and information visualization insights are being applied in areas such as 19. Scientific research, digital libraries, data mining, information graphics, financial data analysis, healthcare. 62. Market studies, manufacturing production control, crime mapping, e-governance and policy modeling, digital humanities data art, organization. Notable academic and industry laboratories in the field are Adobe Research, IBM Research, Google Research, Microsoft Research, Panopticon Software, Scientific Computing and Imaging Institute, Tableau Software, University of Maryland Human Computer Interaction Lab. Conferences in this field, ranked by significance in data visualization research. 63 are IEE Visualization, an annual international conference on scientific visualization, information visualization, and visual analytics. Conference is held in October. ACM SIGGRAPH, an annual international conference on computer graphics, convened by the ACM SIGGRAPH organization. Conference dates vary. Conference on Human Factors in Computing Systems CHI, an annual international conference on human-computer interaction, hosted by ACM SIGCHI. Conference is usually held in April or May. Eurographics, an annual Europe-wide computer graphics conference, held by the European Association for Computer Graphics. Conference is usually held in April or May. For further examples, see category, computer graphics organizations. Data presentation architecture. A data visualization from social media. Data presentation architecture, DPA, is a skill set that seeks to identify, locate, manipulate, format and present data in such a way as to optimally communicate meaning and proper knowledge. Historically, the term data presentation architecture is attributed to Kelly Lott. A data presentation architecture, DPA, is a rarely applied skill set critical for the success and value of business intelligence. Data presentation architecture was of numbers, data and statistics in discovering valuable information from data and making it usable, relevant and actionable with the arts of data visualization, communications, organizational psychology and change management in order to provide business intelligence solutions with the data scope, delivery timing, format and visualizations that will most effectively support and drive operational, tactical and strategic behavior toward understood business or organizational goals. DPA is neither an IT nor a business skill set but exists as a separate field of expertise. Often confused with data visualization, data presentation architecture is a much broader skill set that includes determining what data on what schedule and in what exact format is to be presented, not just the best way to present data that has already been chosen. Data visualization skills are one element of DPA. Objectives. DPA has two main objectives. To use data to provide knowledge in the most efficient manner possible, minimize noise, complexity, and unnecessary data or detail given each audience's needs and roles. To use data to provide knowledge in the most effective manner possible, provide relevant, timely and complete data to each audience member in a clear and understandable manner that conveys important meaning, is actionable and can affect understanding, behavior and decisions scope. With the above objectives in mind, the actual work of data presentation architecture consists of creating effective delivery mechanisms for each audience member depending on their role, tasks, locations and access to technology. Defining important meaning, relevant knowledge that is needed by each audience member in each context. Determining the required periodicity of data updates, the currency of the data, determining the right timing for data presentation, when and how often the user needs to see the data. Finding the right data, subject area, historical reach, breadth, level of detail, etc. Utilizing appropriate analysis, grouping, visualization, and other presentation formats related fields. DPA work shares commonalities with several other fields, including business analysis in determining business goals, collecting requirements, mapping processes. Business process improvement in that its goal is to improve and streamline actions and decisions in furtherance of business goals. Data visualization in that it uses well-established theories of visualization to add or highlight meaning or importance in data presentation. Digital humanities explores more nuanced ways of visualizing complex data. Information architecture, but information architecture focuses on unstructured data and therefore excludes both analysis in the statistical data sense and direct transformation of the actual content data for DPA into new entities and combinations. HCI and interaction design, since many of the principles in how to design interactive data visualization have been developed cross-disciplinary with HCI. Visual journalism and data-driven journalism or data journalism. Visual journalism is concerned with all types of graphic facilitation of the telling of news stories, and data-driven and data journalism are not necessarily told with data visualization. Nevertheless, the field of journalism is at the forefront in developing new data visualizations to communicate data. Graphic design, conveying information through styling, typography, position, and other aesthetic concerns. Analytics. Big data. Climate change art. Color coding and data visualization, computational visualistics, information art. Data management. Data physicalization. Data presentation architecture, data profiling. Data warehouse. Geovisualization. Grand Tour Data Visualization, IMCFA-MOS, 1987, Graphical Data Analysis, Infographics. Information Design. Information Management. List of graphical methods. List of information graphics software, list of countries by economic complexity, example of tree mapping. Patent visualization. Software visualization. Statistical analysis. Visual analytics. Warming stripes. A. The first formal, recorded, public usages of the term data presentation architecture were at the three formal Microsoft Office 2007 launch events in DEC, Jan and February of 2007-08 in Edmonton, Calgary and Vancouver, Canada, in a presentation by Kelly Latt describing a business intelligence system designed to improve service quality in a pulp and paper company. The term was further used and recorded in public usage on December 16, 2009 in a Microsoft Canada presentation on the value of merging business intelligence with corporate collaboration processes. Sometimes known as a representation for data visualization, in which the data is represented by symbols, such as bars in a bar chart, lines in a line chart, or slices in a pie chart. 1. A chart can represent tabular numeric data, functions or some kinds of quality structure and provides different info. A pie chart showing the composition of the 38th Parliament of Canada. The term chart is a graphical representation of data has multiple meanings. A data chart is a type of diagram or graph that organizes and represents a set of numerical or qualitative data. Maps that are adorned with extra information, maps around, for a specific purpose are often known as charts, such as a nautical chart or aeronautical chart, typically spread over several map sheets. Other domain-specific constructs are sometimes called charts, such as the chord chart in music notation or a record chart for album popularity. Charts are often used to ease understanding of large quantities of data and the relationships between parts of the data. Charts can usually be read more quickly than the raw data. They are used in a wide variety of fields, and can be created by hand, often on graph paper, or by computer using a charting application. Certain types of charts are more useful for presenting a given data set than others. For example, data that presents percentages in different groups, such as satisfied, not satisfied, unsure, are often displayed in a pie chart, but may be more easily understood when presented in a horizontal bar chart. 2. On the other hand, data that represents numbers that change over a period of time, such as annual revenue from 1990 to 2000, might be best shown as a line chart. Features. A chart can take a large variety of forms. However, there are common features that provide the chart with its ability to extract meaning from data. Typically, the data in a chart is represented graphically since humans can infer meaning from pictures more quickly than from text. Thus, the text is generally used only to annotate the data. One of the most important uses of text in a graph is the title. A graph's title usually appears above the main graphic and provides a succinct description of what the data in the graph refers to. Dimensions in the data are often displayed on axes. If a horizontal and a vertical axis are used, they are usually referred to as the x-axis and y-axis. Each axis will have a scale, denoted by periodic graduations and usually accompanied by numerical or categorical indications. Each axis will typically also have a label displayed outside or beside it, briefly describing the dimension represented. If the scale is numerical, the label will often be suffixed with the unit of that scale in parentheses. For example, distance traveled m is a typical x-axis label and would mean that the distance traveled, in units of meters, is related to the horizontal position of the data within the chart. Within the graph, a grid of lines may appear to aid in the visual alignment of data. The grid can be enhanced by visually emphasizing the lines at regular or significant graduations. The emphasized lines are then called major grid lines, and the remainder is minor grid lines. A chart's data can appear in all manner of formats and may include individual textual labels describing the datum associated with the indicated position in the chart. The data may appear as dots or shapes, connected or unconnected, and in any combination of colors and patterns. In addition, inferences or points of interest can be overlaid directly on the graph to further aid information extraction. When the data appearing in a chart contains multiple variables, the chart may include a legend, also known as a key. A legend contains a list of the variables appearing in the chart and an example of their appearance. This information allows the data from each variable to be identified in the chart. Types. Common charts. 4 of the most common charts are histogram, bar chart, pie chart, line chart. This gallery shows. A histogram consists of tabular frequencies, shown as adjacent rectangles, erected over discrete intervals, bins with an area equal to the frequency of the observations in the interval, first introduced by Carl Pearson. 3. A bar chart is a chart with rectangular bars with lengths proportional to the values that they represent. The bars can be plotted vertically or horizontally. The first known bar charts are usually attributed to Nicole Oresme, Joseph Priestley, and William Playfair. 4. A pie chart shows percentage values as a slice of a pie, first introduced by William Playfair. 5. A line chart is a two-dimensional scatterplot of ordered observations where the observations are connected following their order. The first known line charts are usually credited to Francis Hauksbee, Nicolaus Samuel Crupius, Johann Heinrich Lambert and William Playfair. 6 other common charts are timeline chart, organizational chart, tree chart, flow chart, area chart, cartogram, pedigree chart, radial tree. Less common charts. Examples of less common charts are bubble chart, polar area diagram, waterfall chart, radar chart, tree map, stream graph, gap chart. This gallery shows. A bubble chart is a two-dimensional scatterplot where a third variable is represented by the size of the points. A polar area diagram, sometimes called a coxcomb chart, is an enhanced form of pie chart developed by Florence Nightingale. A radar chart or spider chart, or joy, is a two-dimensional chart of 3 or more quantitative variables represented on axes starting from the same point. A waterfall chart, also known as a walk chart, is a special type of floating column chart. A tree map where the areas of the rectangles correspond to values. Other dimensions can be represented with color or hue. Smaller areas go to the bottom right corner. A stream graph, a stacked, curvilinear area graph displaced around a central axis. A gap chart, a time series chart showing evolving gaps and inequalities between series. Other dimensions can be represented with color or hue. Field-specific charts. Some types of charts have specific uses in a certain field. Open high-low close chart. Candlestick chart. Kaggle chart. Sparkline. This gallery shows. Stock market prices are often depicted with an open high-low close chart with a traditional bar chart of volume at the bottom. Candlestick charts are another type of bar chart used to describe price movements of an equity over time. A Kaggle chart is a time-independent stock tracking chart that attempts to minimize noise. Alternatively, where less detail is required and chart size is paramount, a sparkline may be used. Other examples. Interest rates, temperatures, etc. at the close of the